NiCd pack has now been charging for more than 24 hours, and I actually charged it on a bit more than the 220 about milliamps that I started with. I charged it on about 350 milliamps for some hours to see if I could raise the voltage on this. Because this actually is, if we count the cells here, you will see that this is 10 cells, and 10 cells of 1.2 volt each is 12 volt. But each of these cells, when they are fully charged, is a bit more like 1.25 volts or something. And I will try to move my scope meter like so. Yeah, it might be possible to see that. This actually is 10.41 volt. And that means there could be several damaged cells, but I don't think so. I think it's just one cell that is not giving out any voltage here. And that means we have to take this pack apart to, yeah, maybe salvage it by fixing that cell. And how we best go about to open this, I am not sure. You have this band that goes here, and you have this way, but I think the safest bet will be to, yeah, maybe try to, this is the band I'm cutting against now. I can do the same on top, but maybe we can just pry this open now. I will try to salvage this top sticker. That was the top part, and inside here you can see there are some glue and stuff here, and maybe that can give us a clue. And here you can see that some of the cells has started to leak. It's not very clear, but I can zoom in on this. Actually this way. So we can see here that there are some slight corrosion here. This is not just dust. But we can try to measure out the cells and see what we kind of get here. And here we can see it's even worse. Here you have this bits of corrosion. It's almost like wool that's on this, so it looks like a sheep has been inside here. And this cell measures at 0 volt. And this also measures at 0 volt. Most of the cells actually measure as 1.3 volt, but this one measures out to about 0, and this one measures out to about 0. So we have 8 of the cell actually giving a result for us. NiCds like this is not possible to get anymore because of environment restrictions, and of course it's not wise to use NiCds anyway. Other cells will give similar voltages like this, but they do require a slightly different charging regime, as NiCds are quite forgiving and you can about charge them any way you like. with trickle current, with sine waves, with other stuff, as long as you don't reverse the polarity. But the NiCds are often in these old circuits just charged with current, like I did when I tested this. That's not something we can easily do with other cells like NiMH cells. So, is it possible to salvage this? Yes, of course I can change just the cells that's broken and glue this in and use it, because the other cells actually will work, but I don't think it will be a good solution, so I have to think about something else to test this. But these cells are just 2200 milliamps each cell, and you don't need a very large cell to get 2.2 amps today. When it comes to rechargeable batteries today, it's the NiMH battery that is the standard. And here you have AA batteries that have 2100 milliamps, and they have these ears here for soldering so that you don't have to use any special tools. And they also have batteries with higher capacity than this, but that will be more specialized batteries. But what we can see here is that they have a sub-C battery with 2200 milliamps, and this is a C size in diameter. And if we go for a good standard size C battery, you can have 3000 milliamps or you can have 4000 milliamps. So that means this has almost twice the power density as the one that was in this computer. But it will be rather expensive to burn away this much money on just a battery pack that probably is just going to be used once a year or something like that. So I will try to see if I can find a cheaper solution. And here you have 2100 milliamps, 4 batteries for about 200 Norwegian krona. And that means I have to buy 3 of these packages, so it means it will be 600 krona if I choose this solution. And you can probably go even cheaper. We can try Elkjøp. Yeah, but now we're talking. Here we have 4 cells, 2000 milliamps, 439 krona. And you have the same cell with 2600 milliamps for 179. So this is probably among the cheapest we can get this. I can check one more place. Yeah, now we're talking. 105 krona excluding wet, that's about 130 krona, 131, and it's 2600 milliamps and a piece of 5. And they have this 2000 for 95 for 4, and you have some smaller Duracells. Yeah, they have some other variations here too, but I think I just will go and see what I have lying around. It's not optimal to use NiMH cells anyway, so I will just try to look into my old stock inventory. Yes, and see what we have here. This is a battery from a DeWalt 12-volt drill. I have actually several of these drills, and they each use this kind of package. And it's only these models of Black & Decker and DeWalt tool that uses this exact battery. And there are some small differences on this. The one that's called Black & Decker is 1.3 ampere hours, and they have the same battery. This is a NiCd cell. And they have the same cell in nickel metallurgy, NiMH, and that cell is 2.6 ampere hours, so that's maybe the same cells that we was looking into earlier. But this battery, I know it's working because it's not long ago I tested it in a drill. I have several of these that's not working. But this one gives out 13.1 volt approximately, and it should work, but I'm not sure what capacity this battery has after all these years, This battery is, after all, not as old as the laptop, of course, but we are talking about maybe 8 or 9 years old, this battery. We also have some space constraints if you are going to use this inside the Tandy as a replacement battery and not have this strapped to the outside like some appendix. So I will try to open this battery and then I will charge this battery and test the remaining capacity. Yeah, that was one solid wire, and we can see that this is actually glued together in a different configuration than on the Tandy battery. And you can see it's only 9 cells down here, and the 10th cell is actually this one that stands inside the plug. I didn't notice that at once. That means to test this, I'm first just going to try to charge this, and then I will try to discharge this battery in a similar fashion as the Tandy. We have some information here, actually have several figures. We have the battery that stated that it's 12 volts and it's 2200 milliamps. And on the back of the computer, or on the underside, it said 750 milliamps power consumption. We also have from the user manual that this battery should last 4 hours. And if this battery is going to last 4 hours, you have to drain this battery over 4 hours. And that means that you have about 550 milliamps. But that is of course under ideal circumstances. So to test this battery, how long it lasts, I'm going to discharge this battery with about 400, we can say 500 milliamps discharge on this. So I'm just going to charge this battery good and well. And tomorrow I will take and connect this to a resistor. That means I can drain this battery with 500 milliamps as long as the voltage is 12 volt. And that is of course not true, because it will have this kind of discharge. When this is fully loaded, it will maybe be 13.5 something. It will start here on 13.5 and it will drop slightly until it cuts rather abruptly here. So maybe here it will be 12 volts and maybe here it will be 10 point something down here. But as a mean value, it's not wrong to use 12 volt, and that's also the marking value of the battery. So the resistor, we need to do this. And this should of course go in amps, so it's 0.500 amps. And when you take 12 volts and divide it by 0.5, you get 24 ohms. So that will be the resistance, but 500 milliamps in 12 volts is quite the wattage. So this needs to be a rather big resistor. And then you have the voltage times the current, that is 0.5. So that means you need a 6 watt resistor. So that will be a rather large resistor. So we need a 24 ohms, 6 watt resistor to test this battery pack. And how are we going to do that? I'm not sure yet, but I will find some values. We might take a bunch of resistors in parallel. And to charge this, I'm going to use my power supply as we saw earlier. And this is a battery that can handle larger charge. And I have to find out what's positive and what's negative on this. And this is the positive lead. It's the one that goes into here. So that will be that one. Supply. like so. And what we will do, this battery is 2 amp hours. If I charge that with 2 amps in 1 hour, of course will be very hot. But I can charge it with a tenth of that for 10 hours. And that will be the same equivalent. So 200 milliamps in 10 hours minus the heat that will be dissipated in this battery will be the formula. So I will do 220 milliamps into this battery. And then I leave this for tomorrow morning, and we will connect a resistor to this battery and we will discharge it till it reaches about 10 point something volt. Yes, now the battery is fully charged, and we have to discharge this to a 24 ohm resistor as we agreed upon last night. And this is the power resistors that I just found and grabbed them in my storage. And these are 120 ohm resistors, and they are 5.5 watt each. And I also have some 220 ohm resistors, that's about 3 watt each. So it's 220 ohm with 3. But as the value we are searching for is 24 ohms, this will be a really simple circuit. We just do it as simple as this. And we have to remember that even though a resistor is marked for 5.5 watt of heat dissipation, it will get very hot. The specification is just that it will handle that kind of heat dissipation. If we make this circuit like so, 120 ohms times 5 over here, the resulting resistance will be exactly 24 ohms. And that is, when you have the same resistance in each resistor, it will be the simple equation like so. And when each of these can handle 5.5 watt, the whole circuit will handle about 27 watt. And as we said last night, the total heat dissipation that we will have here is this simple equation. It's 12 volt times 0.5 ampere, and it's 6 watt. And that will be easily handled by this, and each resistor will not get overly hot. I will just solder this into a heap of resistors, and we can test this battery that now has been charging overnight. And the open terminal voltage is 13.1 volt. So that's okay, a bit low, but this has been now standing without charge for some time. And we will discharge this till it reaches about 10 volt or something. If I would do this in a real life application and should dissipate that much heat, I might want to do it by making some room between these resistors to make the heat go away faster. Or even if you're making some kind of heating element, you want there to be an airflow around the heating element to dissipate the heat to where you will need it. This is very old resistors. I probably had them lying around for more than 30 years, and good knows how long before that they was manufactured. Now the resistance in this is 23 ohms about, and that's within the specifications for this. These resistors will also increase in resistance when they are heated, I think. Yes, this is the setup, and it's actually running now. I will try to twist this to get some less reflection on the scoop meter, and I have to measure from this one and into this clip here for the voltage, and it's 12.79 volts, and we have about 470 milliamps. And this is getting quite hot. It's not burning hot, but of course it drains 6 watts of power about. That is 6 watts of power. So we just have to drain that, but I will go and get some stone tile to put beneath the resistors. This might break the measurements for a while. But like so, then it don't burn anything. Yeah, and this is when I realized that I didn't put the clock in the picture. This clock was started 10 minutes on 13, that is 12:50. You can see that the voltage is dropping, and as the clock is ticking, we are fast forwarding something on the time here, but it's dropping not rapidly, because this is the flat point of the curve, and the main capacity of the battery should be drained before we go beneath 12 volt. And now we try to measure the heat that is dissipated on this, and you can see it's from about 50 to up to 100 degrees on this resistor, and of course the part where less air, it's measured the hottest. And now when we are at the end of the discharge curve, the battery is draining faster, and we can see now it's only about 5 minutes from when it's 11.3 volt till it drops below 11 volt, and when it comes down to 10.5 volt, it actually drops with 100 millivolt each second, so this will be down in 10 volt in quite the short time. But you know what? I will call this a success, because now it's 10.3 volt and it's exactly 4 hours since I turned this on. And since this is a 8 or 9 year old battery, I will call that a stunning success, and I think this battery will be more than adequate for powering the Tandy for 3 hours with moderate use of the floppy drive. Before I do anything else, I will just put this battery back together, and I will solder on some leads to connect this to the Tandy straight as it is. Hope you enjoyed the content, and hope to see you again in my next episode in this probably 3 or 4 part series. Hit subscribe if you want to be notified when I post another video. Thanks for watching.